Hello Chem students, I'm going to do the second lecture of SN2, E2, SN1, E1 reactions. I posted the first one already. These are pretty long lectures. I'm sorry for that. Maybe you can skip around if some of it seems not that important to what you need and find the parts that are more helpful to you. Okay, so let's go ahead and get started. So last time we were looking at SN2 reactions and E2 reactions to make different functional groups. A real important functional group for us is an alcohol right here. And we had sort of a problem with hydroxide at secondary centers. So I have a carbon here with a bromine that's a secondary. I would like to do an SN2 backside attack to make the alcohol. But mostly what we get is the alkene and a little bit of alcohol. So we need a way around this. It turns out that there are ways around it, and so a way for us will be to use a different kind of oxygen. So you'll notice this is an oxygen minus, like the oxygen minus up here, but this oxygen minus is really stabilized well by resonance since it's spread over two oxygens. It's much more well behaved in the SN2 reaction and does an SN2 reaction backside attack, so you can see that the stereochemistry is opposite now. And so this is good in that it gets the oxygen onto that carbon, which is what we want up here with the alcohol. However, this is not an alcohol, this is an ester. An ester may be a great product for some reactions, but in this case we want the alcohol. So we need a way to clip off this part right here, and we do have a way. There's more than one way, but we'll just take a look at one on the next slide. Okay. Oh, just a reminder, the reason that the hydroxide does more E2 is because it's much more basic. So remember, the conjugate acid of an alcohol or water is about 16, and the conjugate acid of a carboxylic acid is pKs 5. So what we're going to do is we're going to take hydroxide again, and this time we're going to present it with the ester. Now there's a little bit of ambiguity here because it seems like there's two targets. We have a carbon attached to oxygen, which should be partial positive, and we have a carbon over here attached to the oxygen, which should be partial positive. So if we look at that, we have two targets. The hydroxide we've already seen can attack this kind of a carbon when there's a bromine there, but that was the only target when the bromine was there. Now we have two. If you look at this carbon, it has three bonds to oxygen, the double bond O and the single bond O. It might seem reasonable that this is more partial positive, and maybe the negative should be attracted there more. If the oxygen did come over here and attack this carbon, we have a good place to push electrons away onto the other oxygen that will give us a minus oxygen coming from a minus oxygen. So it turns out this is a real important reaction that we're looking at. It's a new mechanism than what we've already seen, so you'll have to learn this too. And it's pretty common, so it'll appear in other places. Okay, so let's take a look. Now the first people who came on the scene to figure this out had a dilemma because they didn't know which carbon got attacked. And so what they did was they stuck an oxygen 18 in the middle, which is just a tiny bit. That's like 0.2% of oxygen. But they put it right here in the middle. So if the oxygen attacked the carbon on the right up here, this oxygen would leave and stay with the carboxylate part. But if this hydroxide attacked the carbonyl and this was pushed away, then the oxygen 18 would stay with the alcohol part. So that was the way that they were going to solve it. And what they found was that after the reaction was over with hydroxide, the oxygen 18 was on the alcohol part and not the carboxylic acid part. So that sort of tells us that the oxygen attacked the carbonyl. So this is a mechanism now that you want to learn. You want to practice this. It's going to appear a lot of times. Even in this lecture, I'll do it more times. But so the way the reaction occurs is the hydroxide, which is a very good nucleophile, as we have seen, attacks the carbonyl carbon. And because of the double bond, we can shift the electrons over to the oxygen and put the minus charge up here. Now this carbon has become tetrahedral. Okay, over here it was trigonal planar. So in this intermediate, which only lasts for a very short time, this is called a tetrahedral intermediate, sometimes capital T, capital I, intermediate. Now this O minus can push back to remake the double bond O, because that's a very stable feature. But if it pushes back, we have to get rid of some electrons. Now we have two groups here. We have the O minus from the alkoxide. We have the O minus from the hydroxide. If we push back and kick off hydroxide, we just go back to the start, so we kind of ignored that one. But if we push off and kick off the alkoxide, okay, the alkoxide now is much more basic than the carboxylate conjugate base of the acid. And so it will take the proton away and make the alcohol and leave us with a much more stable carboxylate minus charge. So you can see in the course of this reaction going all the way over here, we take the minus from the hydroxide, much less stable than the minus on the carboxylate. And so this is a very favorable reaction. This now gives us the alcohol that we wanted before, but we had to do all this extra work to get there. And that's the way it is sometimes. Okay? Even though in your imagination you could imagine the reaction would work really well, in reality it might not work well, so you need an alternative approach. This whole process here is called acyl substitution, okay, to attack that carbonyl. I wrote out the mechanism again here, just in a series of more obvious steps. So we have an ester with the hydroxide, okay, aqueous hydroxide. The hydroxide would tend to attack the carbonyl. We push up. Here's our tetrahedral intermediate. The O minus up here pushes back. It could kick off either group, but the group that we focus on is the alkoxide. The alkoxide is much more basic than the conjugate base of the acid down here, so it steals away the proton, gives us the alcohol that we wanted, and if we work this up, just a mild neutralization of the base with a little bit of acid, then we can actually get the carboxylic acid too, in this case ethanoic acid. So in some cases this might actually be the product that's desired. Up here I'm focusing on the alcohol, getting to the secondary alcohol, but in natural products there might be a real simple alcohol and a very complex carboxylic acid that's important, so this would work either way. So our original goal was to take this bromoalkane and make it into this alcohol, but because the hydroxide is too basic, we got all this elimination product that we didn't want. So instead we used the carboxylate. Remember, I give you acetic acid. That's one of the things I give you in your toolkit, and we would have to use sodium hydroxide to pull that proton off to make this. So now we have our strong base nucleophile, very well behaved SN2 at secondary center, and then we have to come along and use hydroxide to do the acyl substitution by attack here. So those are all steps you should have well worked out in your thinking for organic chemistry, because it's really common in a lot of places. Here's some of the other places that we could think about it, and there'll be more, but what I did here was I put an anhydride with hydroxide. I put an ester, we just did that one, with hydroxide. I put an acid chloride with hydroxide. I put an amide with hydroxide. And down here, finally, I have a carboxylic acid, which behaves a little bit differently with hydroxide. So in all these steps, the first four, we have acyl substitution, just like we saw before. So you should be able to generalize what we just did for these. I have some of those on the next slides. So for the anhydride, we have two targets. So I'm attacking this particular target with a smaller group, the methyl versus the R group. So I'm attacking over here. We make a tetrahedral intermediate. We push back down and kick off the carboxylate in the anhydride. This will be a very stable minus charge. Since we're in base, we would immediately strip off this hydrogen here, and we would end up with two different carboxylates. Mild acid workup would give us the carboxylic acids over here. I showed them both going to the same proton, but of course those would be different protons, different H3O pluses, just to show the final step. So we would get two different carboxylic acids. It might turn out that both of those are useful, or maybe only one of those is useful, but in that case, we would worry about it then. All we're doing here is just showing how it works. For the amide, we would do sort of the same thing. We take the hydroxide, we attack the carbonyl, push up, push back and kick off the nitrogen minus. Now this is going to be a little slower elimination on this one, because the O minus would be favored because it's oxygen's more electronegative. But if we force it a little bit, then once in a while the N minus can leave. You might have to heat this up a bit. and then the N minus or the hydroxide minus could come over and take that proton. Okay, and then in the final workup, we would protonate these two guys, mild acid neutralization. Okay, so we could, actually it would probably be better to use the N minus right here because it's more basic than the hydroxide here. Now we're going to look at the E2 reaction in a more systematic way. We've just been talking about the anti-C beta H and C alpha X, but there can be a whole lot of anti-C beta H's, so we're going to take a look at that. If we had a methyl group, methyl X, so bromomethane, can't do an E2. You have to have two carbons to do an E2. All we can do here with a strong base nucleophile is SN2. However, if we go to one C beta carbon, there are three additional sites here. They could all be hydrogen, or two of them could be hydrogen, or one of them could be a hydrogen. And in those cases, we could do an E2 reaction. Now remember, if this is primary, SN2 is the major product that we expect, except for T-butoxide, which is big and bulky and basic. Okay? So we'll look at specifics in just a minute. If I had a secondary bromoalkane, SN2 is going to slow down a little bit, so E2 is going to become more competitive. If the nucleophile base is well behaved, like we just saw with the carboxylate, then SN2 can be the major product. But if the nucleophile base is pretty basic, like the hydroxide or an alkoxide, then E2 is the major product. So we'll have to be concerned about that. But in any case, I could have a lot of places for hydrogen here. They could all six be hydrogen, or 5, or 4, or 3, or 2, or 1, or even none of them could be hydrogen. That's a possibility too. Okay, so in those cases where we have a C beta H, we could do an E2. If we went to the tertiary center, then the only reaction we have with a strong base nucleophile is E2. And we got a lot of positions that could be hydrogen. If all 9 were hydrogen, it would actually be a pretty easy problem, because then any one hydrogen you looked at would be equal to all the other hydrogens. The problem comes when they're not all the same, and then you got to consider each one sort of individually. Worst case scenario would be I have a different group on each carbon and then 2 hydrogens, and then the 2 hydrogens could be E or Z, E or Z, E or Z. And if the third group on each of the C betas was different, then all of those would be different answers. So that would be a worst case scenario. Now, what I have shown here is just a single C beta H, C alpha X, and everything else has been made general. Okay? Now, I've marked them here so that you can see there's some differences in the products that result over here when we have this particular conformation. So if we have a strong base nucleophile, the only way this reaction can work is anti-C beta H, C alpha X, because they're staggered and the orbitals are parallel, which they have to be to make the pi bond. Okay? Now, for this molecule, I picked 2 different hydrogens here that we can tell the difference between. One is hydrogen and one is deuterium, which is also hydrogen, but it has an extra neutron that we can distinguish. So in this case, I have the hydrogen, the proton, anti, so the base picks that off, and you'll notice that D remains in the molecule over here, and D will be opposite to R4. Okay? So if I classify R3 higher than R4, R3 higher than R4, then these 2 guys would be the highest priority groups, and this would be a Z alkene. However, I can rotate around this bond right here between C alpha and C beta, and I can bring the deuterium up here, put the hydrogen in the back, bring R1 out to the front. Now if I lose the deuterium, anti-C beta D and C alpha bromine, then I'll get a different alkene. First off, there's no more deuterium because we took it off. Also, R1 is out in front with R4. And we just said that R3 is higher than R4. Okay, so if R3 is higher and R1 is higher, then this is an E alkene. Now if I come up here and switch these 2, then I would get the totally opposite result. Okay, there would be no, I would lose deuterium here, and so I'd have hydrogen here, and it would be Z. So you can see it's real important, the stereochemistry of these 2 centers. And if these are both chiral centers, then we have 2 to the 2 equals 4 possible stereoisomers. Okay, so this is what I call a vertical view. I'm picking off the proton, it's kind of straight up, and CX is straight down. This is what I call a horizontal view. It's really the same reaction, so I won't go through all the details here, but again, pick off the proton, use these electrons to make the pi bond, and push X away. I can rotate D anti and do the same thing to get this result over here. Okay. Just to mention here, I know this can sometimes seem complicated, but in reality this is pretty simple. You can't get much more simple with all the possible details that are there than just having two hydrogens on one carbon to look at it. And so I just refer to these as mini examples of nature. Okay, nature compounds are way, way more complicated, but you need to understand this to understand those more complicated molecules. All we do in the complicated molecules is we just focus on the one little part that's going to react and try to convert it into something like this. Now we're making a lot of alkenes, so we have to become familiar with what are the most stable alkenes. And so the patterns are shown here. There's a little bit of logic to this. Some of the arguments are too complicated for us. We'll just use the fairly simple-minded argument that works pretty well. Okay, so the first alkene I have here is the kind of the parent alkene. Everything is hydrogen. So this is unsubstituted ethene. Common name would be ethylene. Now if I come along and replace any one of these hydrogens with an R group, so methyl, ethyl, propyl, whatever I want, okay, with an R group. Now this is what we call monosubstituted alkene down here. Now this actually makes the alkene more stable. Okay, as we'll see, there's an inductive donating effect that helps stabilize the pi bond. If I come along and put a second R group, there's three ways I can do that. I can put the second R group on the same side at the other carbon, and we call that one cis. We would actually say Z. Or I could take that second R group and put it over here on the same carbon. We would call that geminal. Gemini from astrology would be twins, so these are kind of twin groups. Or I could come along and take that second R group and put it all the way across on the other carbon. We would call that trans. Now the geminal and the cis are about the same in terms of stability, but the trans is better. Trans is more stable, because if this is a big R group, it's better to have the other big R group on the other side. If I put them together, they crowd each other, and we get a little electron-electron repulsion there that destabilizes the molecule a tiny bit. If I come along and put a third R group on, it doesn't really make any difference where we put it here. So I have three R groups. Notice there's only one hydrogen left. This is more stable. And if I put on four R groups, this is called tetrasubstituted versus trisubstituted. And this is even more stable. Okay, so these are just kind of general tendencies. There are exceptions if we do certain things, but we're just looking at the general tendencies. Now our argument is going to be just a very simple-minded argument. Remember, sp2 carbons are more electronegative than sp3 carbons because they're 1/3 s, and the sp3 carbons is 1/4 s. And the s electrons are more electronegative, and if the R group inductively donates to that, that helps this carbon in this pi bond. So that's our kind of a simple-minded argument. Okay, so every time we put an R group in place of the hydrogen, the double bond gets a little more electron density pumped in to help stabilize it. So let's take a look down here. You might want to stop the slide for just a minute and think, which of these alkenes is the most stable? So I'll just wait just a tiny bit to give you a chance to stop it and make your guess. Okay, so now I'm going to tell you the answer. So if I look at this first alkene, I see that it's disubstituted, and they're on the same carbon. So we would call that geminal. If I look at this alkene, again, it's disubstituted. They're on opposite sides, so that would be trans. So trans would be more stable than geminal. If I look at this alkene, I see there's only one R group, so this would be monosubstituted, and that would be less stable than any of the other ones. If I look at this alkene, I see it's 1, 2, 3 trisubstituted. There's only one H here, and this would be more stable than any of the first three. If I look at E, it's again disubstituted with cis, and you can see the two bigger groups are on the same side, so that's going to crowd each other. So this one will be less stable, certainly, than D, but also less stable than B. Okay. Now, this is a little more tricky problem here. So which alkene is more stable? A, B, or are they similar in stability? So again, you could stop the slide and make your guess. Okay, I'll wait just a second, and then I'm going to give you the answer. Okay, so if I look at this alkene, I see it's 1, 2, 3. It's tri-substituted. And if I look at this alkene, 1, 2, 3, I see it's tri-substituted. So you might be tempted to say they are similar stability, but that would be wrong. When I look at the size of the groups, I see an ethyl on the side with a methyl. These groups are going to crowd each other. And over here I see an ethyl on the side with an ethyl. These are bigger groups, and so they will crowd each other more. And so the answer will be A, because of the size of the groups that are bumping into each other. Okay, so now a couple more questions as we go through here. Remember, the first thing we look at is the base nucleophile. I see the minus charge, so I'm thinking this is probably going to be an SN2 or E2 reaction. You can come over here and see the possibilities. Then I look at the R group. I see the carbon with the bromine has 3 carbon groups on it, so that's tertiary. And we have a rule for strong base nucleophiles with tertiary where we say that is only E2. So the answer would be E2. Okay. Our next little question here is how many total hydrogens are on C beta carbons for this compound? And we always start at the C alpha. That bromine marks that carbon. And then we have a C beta up here, and hopefully you can see that's a methyl group with 3 hydrogens. And if I look over here, I have a methylene group with 2 hydrogens. And if I look over here, I have a methine group with 1 hydrogen. So that would add up to 6 total C beta hydrogens. Any of those could be rotated anti and cause an elimination reaction, E2 reaction. So now I'm saying how many different kinds of hydrogens are on the C beta carbons. This is a little more tricky. Well, first off, the methyls are all the same. So those 3 hydrogens are one type. I only have 1 hydrogen here, so there's only 1 type. That's 2 different types. So the question boils down to, is HA the same or different than HB? And it turns out that HA and HB are different, because this methyl group will swing back or forth depending on each of these hydrogens being anti to the C beta, to the C alpha bromine. And so that means there's going to be 4. There's 4 different types of hydrogen. How many chiral centers are present? So if we come back up here and look at this, I have 4 different groups here, so that's a chiral center. I have 4 different groups here, that's a chiral center, and that's it. There are 2 chiral centers. And if I have 2 chiral centers, then how many stereoisomers are possible? That would be 2 to the 2, so there would be 4 possible stereoisomers. So this could be a more involved problem. Okay, there's 4 different ways we could show this in 3 dimensions. So I actually picked one of those over here. You might stop the slides for just a sec and see if you can figure out what is the absolute configuration of these guys. This is not a chiral center, that's a methyl. Okay, this is not a chiral center because that's a methylene. C alpha is chiral, so we could figure that one out. And if we order the priorities, 1 is down here, and then I either have an ethyl on this side or a sec-butyl on this side. Methyl in the back is the lowest priority, which is where we want it. And so the sec-butyl is the second in priority. So I go 1, 2, it's going counterclockwise, that would be S. So if I come over and look at the possible answers, the only ones possible would be A, let me see, yeah, A or B, because those are the only 2 S configurations. So then I have to come over and look at the C beta here. That would be the 4 carbon with the methyl. And so I see the low priority here is up. I would use my arm on this one and point it down. And I see going to the back is 1 and ethyl is 2. So that is also S. So hopefully you got SS, and that would be answer B. So this would be out of the 4 possible stereoisomers, this would be one of them, that is SS. Now you'll notice how I drew it 3-dimensionally. You wouldn't have to actually draw this. What I would do is put in the carbon with the bromine and then put the other 3 carbons just with their bonds with no groups on them. So you would have to put in the groups to fill in the details, but I would give you the 3-dimensional structure. And the reason I draw them anti is so that you can put hydrogens there and then show all of the elimination reactions, the E2 reactions. Remember, it's anti-C beta H pushes off C alpha X. And that would be each case. So I could show 3 different products formed from this particular picture. The only one I can't show is to move HB up. Now watch what happens when I move HB up. Right now the methyl's in the back. But if I move HB up, HA goes to the back and methyl comes out to the front. Okay, so that would be going to end up with a different stereochemistry of the alkene. So that's the 4 possible products we could get. We could take a look at them over here. Okay, so A would be this attack here. B would be attack in the back, and notice they're both hydrogens, so there's not going to be any E or Z on this one. And then C would be attack at the methine carbon, and so that would put the groups like this. You'll notice the 2 larger groups, the ethyl groups, are on opposite sides. That would be E. In this case, the larger group is here and the larger group is here. That would be E. And if I do this one here, where I rotate the methyl to the front and eliminate, then the larger groups are in the front together. That would be Z. Okay, so those are all the possibilities. This is a tri-substituted, this is geminal di-substituted, this is tri-substituted, and this is tri-substituted. So we have 3 of them that are tri-substituted. Again, the most stable would have the larger groups on opposite sides. Okay, so here's a larger group, here's a larger group, and so that would be a better way to arrange it. Now, if I came up and changed some of these configurations, this whole problem would change. I'd have different alkenes down here, but the way it happens is exactly the same. I would just be rotating, like if I switch these 2 groups here to put the different configuration, I wouldn't change the top part at all. I would just change these two groups, and that would give us a different stereochemistry. Okay. What I show here are some templates. I will give you something like this on the exam. Here's side views, and vertical views. Side view, I'm saying we're going sort of horizontal in terms of the X and the C beta H's. Okay. The vertical views, I show C alpha X going sort of straight up and down, and the C beta H is going straight up and down. So these are 2 possibilities. This is the easier type of molecules because I make everything hydrogen. Very simple. The products are very simple for all the different reactions. But over here I've shown it harder, and what I've done here is I put in deuteriums and even a tritium on methyl to make things chiral, to give more stereoisomers that we have to look at, to decide how we're going to fill in the details to get to the answers that we're looking for. So I have those shown here. Again, what I would give you, say something like this, I wouldn't put the D, the R, the H, but I would give you all the bonds that are there. And I would show the bromine here, but leave this blank, and the ends of all the bonds would be blank. You would fill those in from the names. Okay. I put over here some of our nucleophiles, the oxygen ones. But remember, we have nitrogen nucleophiles, we have sulfur nucleophiles, we have carbon nucleophiles, we have hydrogen nucleophiles. So we have all kinds of nucleophiles. And if they have a minus charge, they're strong. And if they don't, they're weak. And so our weak ones are very limited. Water and alcohols, carboxylic acids, but we're going to eliminate those to keep things a little easier. So now I have a molecule I've written out as 2R3S, 2-bromo, 3-deuteriobutane. So if I come down here, butane is going to have 4 carbons, 1, 2, 3, 4. I say it's 2-bromo, so this must be 1, 2. Here's the bromine. Notice how I would write that in for you. You'd have to put the rest of it. And if this is 2R, so the bromine's here, I would come out. Since H is away, I would come out and around. That does look to be R. Okay. And notice I put an H and a D here, and that makes this into a chiral center. So I would hold up my left arm and spread out my fingers. Carbon with the bromine would be 1. Then I'd come over to the methyl, and that would be S. That's what we want, 3S. Good. And notice the base nucleophile has a minus charge, so this would be a very strong nucleophile. And so E2 would be preferred, but we would also get some SN2. So this is kind of the side view. Over here for the vertical view, I changed it a little bit. I put 2R, 3R. So this carbon right here See if I use my hand, my arm is straight up. The carbon with the bromine is number 1 in the back. And I come back to the methyl, that would be R. So that looks good. Okay, so these are just examples of molecules that you would have to show the different reactions. Right now we're only looking at SN2 and E2, but we'll use the same molecule for SN1 and E1 later on. So how many chiral centers? Well, there's 2. Carbon C alpha with the bromine, and then the carbon with the deuterium. How many stereoisomers are possible? 2 to the 2. That means 4. So we could get RR, mirror image SS, or we could get RS, mirror image SR. Okay, what is the nucleophile base? It's strong. What's the RBR pattern? It's secondary. How do they react? Well, with alkoxide, E2 is the major product and SN2 is the minor product. So I have all the reactions shown here, so you can take a look at each one. So here's the 2R3S. Notice by drawing the C beta H as anti, we could put a couple of them into the same picture, but I didn't do that right here. So I have attacking the methyl, all 3 of these would be equal, we would get a monosubstituted alkene. Okay? Notice one of the chiral centers disappears. Nothing happens to the C alpha chiral center. Nothing happens to the chiral center with the deuterium. It stays the same. If I look at number 2, I'm coming down here attacking deuterium with the H here. So I lose the deuterium. Okay, I get the methyls in the E arrangement with no deuterium. If instead I put the H here on the back, and I have to rotate it, so H comes over here, D goes down, methyl comes over here. Notice now the methyls are on the same side. So I lose the H, so the deuterium's still there in the back, the methyls are out here, so this would be Z. And then the SN2 reaction would come in from the back side, always the back side, invert the whole thing over, and so the configuration should change for the C alpha carbon. So in this case right here, bromine coming here, this is R. Okay. And over here the oxygen would be 1 and come out here to the ethyl. That would be going counterclockwise, that would be S. So it does invert. Now the amount of expected product, well, we know that we're saying SN2 is the lowest, so we expect 4 to be at the end. And of these, this is disubstituted and disubstituted. Trans would be most stable, so that would be 2 is the first. So it looks like it would be B. 2 is better than 3, which is disubstituted, which is better than 1, which is monosubstituted, better than SN2, according to our simple rules. This is the other example. So now you can see where I'm going up and down. So same idea. Lose a proton from the methyl. We get this guy here. Lose a proton from this C beta on the side where the deuterium is. We get this result here, the E result. Or we can rotate the deuterium up, the hydrogen to the back, and the methyl out to the front. And if we lose that one, the deuterium's gone. And we have the 2 methyls together on the same side, that would be Z. And then we do the SN2 backside attack that we have there. So if we kind of look back to the previous one, remember in the previous one, what did we say for the molecule that had lost D? Here we have 2Z with no D. If we go back, here we have 2E with no D because we changed the stereochemistry. So that's a tricky little thing that you have to watch for. Alright, now we're going to take a look at a variation of the E2 reaction that's kind of important for us because this is going to be our only way of making alkynes. Now alkyne has 2 pi bonds, so if I wanted to make an alkyne using this strategy, I would have to have 2 leaving groups. Chapter 10 will be able to put 2 leaving groups on, but chapter 9, I just give it to you. So if I use a dibromo compound, dibromoalkane, now I need a super strong base, and I want it to be kind of sterically bulky. For the monobromo compound, we use T-butoxide. But when we do the dibromo eliminations, we use the dialkyl amides. Okay? But everything is the same. Super basic, we're going to pick off a proton, make a pi bond, push away the leaving group, and then we'll do it all over again. Okay, so now I have all the steps shown here, but you'll notice I left out all the curved arrows. So you might want to look at this and think about how each reaction is going to occur. Okay, I have the curved arrows on the next slide so you can see them all, but you want to challenge yourself and test yourself before you get there. Or if you don't know, go look at it and then come back and then try and challenge yourself again after you've taken a look. Okay, so let's take a look. What we see is the very strong base picks off a proton, anti C beta H, C alpha X leaves. So now we have an alkene. So now we could come and do it again. So we pick off the proton, make a pi bond, and it leaves. And now our molecule has become an alkyne. Now remember, alkynes have a little more acidic protons, CH protons, than typical hydrocarbons because they're 50% S. So in fact, this acid has become a stronger acid than the nitrogen acid that we have up here. So this conjugate base is stronger than the conjugate base down here, and so it can strip off that proton. Now that might not be what we want, but we can't stop that. Okay, that's just an equilibrium reaction that's going to favor this. So when we get down here, if what we really wanted was the alkyne, we have to neutralize it with a workup. So we just use mild acid, and then this protonates, and we have our alkyne over here. In this case, this would be ethyne. Common name would be acetylene. But we have a potential here for doing a different kind of reaction. Remember, this is one of our nucleophiles. It's pretty basic, so it's not well behaved at secondary centers. But at methyl and primary, it's a very good nucleophile. So if we have a primary down here, we could come in and do an SN2, and now look at this molecule. We've made a new carbon-carbon bond, and this molecule is 4 carbons long. Okay, whereas we started with 2 up here. And so this is something we can do to terminal acetylides. We can add stuff to them, and we will see other things that can add to later on. So here's a couple other possibilities we will have in this topic, and you'll be able to make in the next topic. So I have a dibromo. That means I can make this into an alkyne. And I have a dibromo, and I look over here, I have some hydrogens. I can make this into an alkyne. So our conditions are 3 equivalents, because we need 1 equivalent to do the E2. We need another equivalent to do the E2, and then we need another equivalent it's going to react with that terminal proton right there. And then we finish this up however we want to do it. So in this case, I just say work up, work up. Okay? And so I would get these alkynes. So notice I started with 3 carbons here, and I have 3 carbon alkyne now, propyne. I started with 2 carbons in the benzene ring, so now I have 2 carbons in the benzene ring, an alkyne. And I'll be able to take off this hydrogen with the dialkyl amide, and I could do the SN2 all over again if I wanted to each of these guys and add more carbons on. Okay, so it just continues. Alright, so we're starting to build up some reactions. We're going to get way more that are coming up. But right now, you want to sort of catalog each type of reaction. We start with something that's a reactant. We use a reagent that you understand to make a product that you can predict. This could be 3 different types of problems. I could give you the reactant and the reagent, and you predict the product. I could give you the reactant and the product, and you predict a reagent. In some cases, we might have 2 or even 3 ways of doing this transformation. So there might not be a single right answer. There might be more than one answer. And then the last possibility is we have a product and you have the reagent, so how could we make that product? And again, there may be 2 or even 3 possibilities for making that product with a certain reagent. Okay. Now, we're going to later on combine several steps like this in a row in synthesizing a target molecule. So TM stands for target molecule, and all we have is that. We have to figure out what could I start with and what could I use to make it. So this is a harder problem because there's 2 things missing. But we have a limited number of reactions. Okay, so by the time we get to the end, we'll have less than 100 reactions, maybe way less than 100 reactions. And so there may be only one way to make something here, or there may be 2 ways, maybe even 3 ways. But you'll be very limited in your choices. It's just a matter of, do you know this or do you not know it? Okay, if you know it, then this is pretty easy. You just keep going back step by step by step until we get to some allowed starting material. But this is only going to work for the steps that you know. As soon as you run into a step that you can't remember or don't know, then you're kind of done. Sometimes you can jump over and try and imagine a starting material to come in from the other direction. but that's usually a lot harder strategy. We always go backwards because we're just going one step at a time. And this is called retrosynthetic thinking, or retrosynthetic strategy, and was developed by a very famous chemist called E.J. Corey, who won a Nobel Prize in the 1990s. So here's some targets. So you might want to look at each of these individually, give yourself a little time, maybe stop the slide and think about it. And you'll notice there's a clue in each molecule. Okay, the hydrocarbon is not the clue. It's whatever the single thing that's there that's different. So my clue is I have an OH. And our question is, how do we get the OH there? Because everything we start with has a bromine. Okay, so this is really pretty easy for us if you think about it. I got an OH there, and what did I start with? I had to have a bromine there. Okay, over here I have an O ester. We've already done this. Okay, we showed this earlier when we were trying to make the secondary alcohol. So here I have an ester, so the carboxylate would be probably the nucleophile, must have a bromine here. This is a little tricky because this is in the back side, and the bromine would have to be on the front side because of the way the reaction occurs. Over here I have an NH2, this is a primary amine. Now this is tricky because to make the primary amine requires that we use an azide. And then we reduce the azide with lithium aluminum hydride, and then we neutralize it with a workup step, mild acid. So this one has a little bit of procedure involved that you would have to be able to write out. Actually 3 different steps, 1, 2, 3. And so forth. Here I have a sulfur nucleophile, that's pretty easy. Here I have an oxygen nucleophile, that would be from an alkoxide. Here I have that terminal acetylide, we were just talking about it. So this is where I made my bond. There must have been a bromine here. Here I have a cyanide, that's nitrile, using this CN, cyanide as a nucleophile. This is really easy because it's right out of the bottle. It shows you exactly the pattern that you need. Okay, here I have a sulfide or a thioether. So I would need a negative sulfur here to attack. There must have been a bromine here. Here I have a deuterium. So this must be nucleophilic deuterium, meaning lithium aluminum deuteride. Here I have a pi bond. That's not a substitution. That's an elimination. So I must have had a bromine at the tertiary center would be best, because then all we get is E2. Okay, and then I would need a strong base like D-butoxide to pull that proton off. Okay, well, let's take a look. So every place I see them, the new group, I put a bromine. All right, so those are our starting materials. This is the only one where there's not really much of a clue because the bromine and the H go away. That's elimination. But everybody else is pretty clearly there's a bromine there. Now, what are the reagents? Okay, here I use sodium hydroxide because it's a primary center. Very good SN2. Here I use sodium acetate, or ethanoate, because it's a very good SN2 at secondary centers. Notice the wedge and the dash. Here I use sodium azide, lithium aluminum hydride, and I should have 3 workup. The workup stands for mild neutralization. Over here I have sodium hydrogen sulfide, good nucleophile. Notice the dash and the wedge because it's SN2 backside. Here I have sodium ethoxide. I would have to make the ethoxide from ethanol and sodium hydride. But that's a very good nucleophile at primary centers, so that would be good SN2. Here I have sodium acetylide, which we made just a couple slides ago. And that would be very good at primary centers, not so good at secondary. Here I have sodium cyanide, very good nucleophile at methyl primary and secondary. So in this case it's secondary. Notice dash and wedge because it's backside attack. Here I would have sodium ethyl thiolate. Okay, so that sulfur has a minus charge. That would be an SN2. Sulfur is very good nucleophile at methyl primary and secondary. Here I have lithium aluminum deuteride. So the nucleophilic deuterium bumps off the bromine. I can't tell if it's backside because it's a primary center. And here I would need some very strong base. So sodium alkoxide would be fine for tertiary bromoalkane. Okay, so here I presented the whole thing again, showing the different reagents and their forms that we would want. I put the little dashes here to show the old bond that broke and the new bond that was made. So this is kind of like your toolkit of reactions. You want to be able to use all the different reagents we have in the different ways that are possible to be able to do these reactions. So again, I show this slide with all these different bromoalkanes, because what I'm hoping you do is that you don't look at each of these individually, but instead you look for the patterns. Here's our unique methyl pattern. Here's a primary, and a primary, and a primary, and a primary. The chemistry for all these guys is going to be very similar. Mostly SN2, except for T-butoxide. And then we have the secondary pattern, secondary, 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 lots of secondaries. And they have a different kind of pattern where E2 and SN2 compete. Remember, more basic and bigger is more E2. Less basic, okay, more stable is more SN2 than E2. And then we have tertiary. Here's a tertiary right here. Okay, here's a tertiary right here. Here's a tertiary right here. And so with strong base nucleophiles, those are only going to be E2 reactions. A couple of exceptions. Primary neopentyl does not react by any route in our course. Secondary neopentyl does not react by SN2, but could do an E2 on this side over here. So that's a possibility. Very reactive are allyl and benzyl patterns. Okay, so we're going to go into SN1 E1 reactions now. These occur by a totally different route, totally different picture or story or mechanism, however you want to refer to it. So you'll notice I have two reactions here that look pretty similar. Okay, I'm using methanol, and I'm using methanol. I'm using isopropyl bromide or 2-bromopropane. Both cases, I make exactly the same product, a methyl isopropyl ether, or I could say 2-methoxypropane. I make an alkene, same ether. Everything looks pretty much the same until we come over and look at the kinetics. So in this case, this is bimolecular kinetics, telling us that the methoxide is participating, and that's because it has a minus charge. Okay? It's very aggressive at reacting with its minus charge. Down here, I do not have that. All I have is the solvent, the methanol. So the methanol is not going to do anything until the bromoalkane reacts. And so we'll see that has to form a carbocation. And when we get over here with a strong base nucleophile, we saw E2 as the major product, and SN2 as the minor product. But on SN1 E1, it turns out that SN1 is the major product, and E1 is the minor product. Okay, so for all our reactions for SN1 E1, SN1 will be the major product, except for one. That will be an alcohol with sulfuric acid and heat. That is the only one where E1 is the winner. So we have all these terms again. You can take a look at them. Hopefully they're very familiar to you by now. Okay. Now, the first step of an E1 reaction is forming a carbocation. So I have a bromoalkane up here. The bromine leaves. Well, bromide's stable. That's great. That's why we use it. But the carbocation is not stable. That's very high energy. So this is hard to form. If we can form the carbocation, then it's going to either add a nucleophile or lose a beta H for the E1 reaction. So when we come down here and look at this, we cannot form the carbocation at methyl. It doesn't have anything to help it, stabilize it. We don't have any R groups to inductively donate. If I put one methyl on there, then I can inductively donate in to that primary carbocation, but that's still not good enough. So the rate for doing SN1 reactions of these guys is way too low. We just say no reaction. Okay, well, this is a good thing, because if you have a neutral base nucleophile, then methyl and primary, there's no reaction. If we come over to secondary, we get to a point where if we form a secondary carbocation, the two R groups inductively donating in helps stabilize it. And so it makes it possible to form. Still not great. Okay, our relative rate is 1. And if we go to a tertiary, that third R group really adds an extra amount of stability. So it makes it much easier to form the tertiary carbocation. And so the relative rate compared to secondary is 1,000,000 times faster. So both of these are possible. We're not going to make a great distinction between them. We're just going to say they both work. And these two do not work. Okay, so here's a picture of a carbocation. This is with the methyl. All the electrons can do in a CH bond is move towards the carbon that's electron deficient. that's not enough to help it. Okay? So actually the positives spread over every single atom when that happens. If I come along and put an R group in there, say a methyl on the side instead of a hydrogen, then each of these bonds can donate towards that deficient carbon, that carbocation. And that helps it a lot, but not enough to make the reaction work in solution for primary carbocations. So this is a good thing, but not good enough. The other thing that can help carbocations is resonance. So if I had a primary carbon, we would say that's not going to react. But if there was an adjacent pi bond, we could have that bromide leave, and the carbocation would get some help from the adjacent pi bond, where it spreads the positive to the other carbon at the other end. And so that's enough to make it possible to make carbocations out of primary if we have this resonance system. Okay, so I tried to draw it a little more three-dimensionally here so that you can take a look. Remember, it's the parallel p orbitals that give rise to that overlap that we call resonance. Other resonance forms would be, say, a carbonyl. If I protonated the oxygen lone pair to the side, then I have the pi electrons here, and I could write this in different ways. I could write the positive on the oxygen, or I could move the electrons to the oxygen and write the positive on the carbon. So remember, that's in the p orbitals. Resonance is always in the p orbitals. So I actually put the proton on the sp2 orbital on the side. That gave the oxygen a positive charge. But then I give these electrons to the oxygen through the p orbital, and then I have an empty p orbital over here on the carbon. Okay, and so this later on, this is going to be very important to us, because we're going to have carbocations from carbonyls, and they're going to do the same thing that carbocations do in this topic. We could turn it around. Say I had a carbocation written like this, and I have an adjacent lone pair. I can borrow those in and write this structure, which would be the better resonance structure, because I have more bonds in full octets. Now, other groups that have this C double bond O, carboxylic acids and hydrides, esters, acid chlorides, amides, aldehydes, ketones, and nitriles even. So if you look at this right here, this is really important because of all these other functional groups that have this same feature. Now, stability of carbocations is pretty straightforward. Methyl, we said, is horrible, and the carbocation energies you see here are in the gas phase. This is really hard to do, but with high energy beams and stuff, they can do this. So we reference, again, the primary guy as the reference point. It's really like 270, but we're going to call that 0. And if we do, then the methyl is 45 above that. So this is horrible, 45 kcal above this. This actually is 21 above the secondary carbocation. And so the primary is too hard for us, but the secondary just starts to work. And if I look at the tertiary with 3 R groups inductively donating in, this drops down to be 38, more stable than the primary. And so you can see it's also more stable than the secondary because of the additional inductive effects of the R groups. Here's a primary carbocation, but it has a pi bond next door, so we have resonance, and that lowers its energy 14, which is just good enough to make it possible. If I have a whole benzene ring here, the carbocation, I can put the positive charge at 3 places, adjacent and across and adjacent. And so the energy is actually 31 kcal per mole more stable than the primary. So pretty stable carbocation, even though it's primary. If I come down here and look at the ability of lone pairs to help out, okay, a lone pair from an oxygen helps it quite a bit. Okay, still this is primary, so I'm kind of looking at this, and I see that the energy is lower 22, so much more stable because of that second resonance structure. If I look at a nitrogen, I would expect it to be better, because nitrogen's more willing to donate, and it is, minus 52. In fact, this is the best positive charge in the whole page here. If I have a sp carbon, so this is what we call an acylium ion, I can borrow electrons, and so these are sp-sp. That is 40 kcal per mole more stable. This sort of looks secondary, so maybe we should compare it up here, but it's definitely more stable than the methyl or the primary. Okay. So let's take a look at our SN1 and E1 reactions. These are multi-step, so they're more complicated. Plus there's more variation in the way the compounds can react. Again, we're going to eliminate the carboxylic acid. We're only going to look at water and alcohols. All right. So these are what we call weak base nucleophiles. If the nucleophile adds to the carbon, then we call it a nucleophile. If the base takes off a C beta H, we call it a base. Okay, so first step, all SN1 E1 reactions start exactly the same. The leaving group leaves. We make a carbocation. This carbocation is going to flatten out because there were electrons here pushing these down, which gave it the sp3 shape. But once those electrons leave, and we have the bromide out here, then they repel each other and go flat. So we have an equal lobe on the top and bottom. Equal empty lobes on the top and the bottom. That is the p orbital. Now, from this guy right here, we have three choices. We will add a nucleophile, or we will lose a C beta H, that would be E1. Adding a nucleophile would be SN1. The nucleophile can add from the top, the nucleophile can add from the bottom, because these are equal lobes. And we can lose the C beta H from the bottom, or we could rotate around and lose it from the top. This is the problem of SN1 E1. It has a lot of possibilities. The third thing that we're going to wait on and not talk about initially is rearrangement. So if I can make a better carbocation from this starting point, then it will rearrange itself to the better carbocation. And if I do that, then the whole problem starts over. So I have a carbocation, it can do three things. Add a nucleophile, lose a beta H, rearrange. If it rearranges, we start over, do the whole same thing again. This can happen several times. So again, this is part of the problem of SN1 E1 reactions. So on the next page, I have the choices. Okay, I have the SN1 choice up here. So you'll notice I attack from the top and I attack from the bottom. This would either be water or this would be an alcohol. If this is water, I would have an OH here in addition to this H. If this was an alcohol, I would have an OR here in addition to this H. So when the nucleophile adds, I'm going to have this extra H here and a positive charge on the oxygen, and I have to lose that. Now notice if I come in from the top, I get one configuration, and if I come in from the bottom, I get the opposite configuration. So if these are chiral centers, I will get both configurations. And we will consider them formed equally, even though that's not always the case. We will just say they racemize, which means 50-50. Now I've redrawn the structure down here in a different way so that we can see the elimination. So notice I've only put one H here to keep track of because I could have multiple H's here or deuteriums and everything could be different for each one. So we're just looking at one. And so for this one H, we could lose it from the bottom so that the electrons come in and form a pi bond in this direction here, and that's going to lock in R3 on the same side as R1. Okay? So coming over here, we would have R3 facing R1 and R4 facing R2. So it would depend on their priorities, whether this is E or Z. Okay? So what do I say up here? Say R1 is higher than R2, and R3 is higher than R4. So R1, so these two are higher priority, this would be Z. But the problem is, with this carbocation, I can rotate this guy around. This is not an E2 reaction where it has to be anti to the leaving group because the leaving group is gone. So I can lose this H from either side. And if I rotate this guy around, okay, then R4 would come out here, R3 would go to the back, and if I lose it this way, R4 faces R1. And so we would get different products. Okay, we would get the E product, losing exactly the same hydrogen. Okay, so you can imagine if there was also a deuterium here, then the deuterium would also give two results. That's going to double up our elimination products from E2. Okay, so just another picture of the same thing. Probably don't need it, but I left it in here. Leaving group leaves, okay, because we have a weak base nucleophile. We have a carbocation, we lose the H from the top, R1 faces R3, okay, or we rotate around, and this time I rotated the R3 and the R4, so R3 is in the back versus the front. Lose the proton, okay, and we get a different alkene. Alright, so you got to keep track of all these details to make these predictions. That's the challenge of this particular topic. Okay. So I always compare carbocations to electron pair vacuum cleaners. They are looking to suck up electron density right here and right here. Okay, so here we have another problem. 2s bromo, 3r deuterio butane. So butane implies 4 carbons. I have those shown here. 2s is going to be a chiral center with the bromine. 3r is going to be a chiral center with the deuterium and the hydrogen and the methyl. We're in methanol, so that's going to be a weak base nucleophile. And so we want to fill in these details. Okay? So you would have to come over here and decide where's 2 and where's 3 and so forth. Let's see what I did. I put the bromine here, so that would be 2. So we're saying 2s. Now you'll notice I put the bromine in the front and the hydrogen in the back. I usually write these the easy way first, because with the hydrogen in the back I can see this right away. 1, 2, 3. I'm going counterclockwise, that would be S. The name says S, so I guessed right. Okay. And then for the other one, I would usually put the H in the back and the deuterium in the front. And if I did that, then I would have 1, 2, 3. That would be R. 2s bromo 3R deuterio. 1, 2. So H is away. I've used my arm, plug it in. 1, 2. It's going R, so that would be correct. So I would have to change it, because if I had H in the back, 1, 2 would be S. So I'd switch these two to make it R. What I would give you is this right here. Okay, so you'd have these blank templates. I'd either give you the horizontal one or the vertical one. So you're going to have to make a decision. When you come up here and look at the bromine, you know that's 1. You know the H is 4. So I have the bromine and the H. H is away, so that makes it easy. So then I have to go for the carbon with the bromine here. That's going to be S. So I'm going to go 1, 2. So when I come down here, I want to go S, which is counterclockwise. Okay, like this. So I got a 1, 2. And so that would be the, this is the carbon with the hydrogen and the deuterium. And this would be the methyl. Okay, down here, I got 1. I would want to go this direction, counterclockwise. And so I would put the hydrogen and the deuterium and the methyl over here. Okay. Now I have a methyl right here in the name, but I just want to point out, I called this butane, but I could have called this pentane or hexane or all kinds of other stuff. And it wouldn't change the problem. The problem is based on the chiral center, these two chiral centers. Okay, if I put other stuff out here, say like an ethyl or a propyl or a benzene ring or something, that's not really going to change this problem at all. So this is butane, this is pentane, this is hexane. I have the bromine and the deuterium in the middle. Notice two chiral centers, two chiral centers. So the point of this is that not only can I change the absolute stereochemistry up here with 4 different stereoisomers, I could also change the name of the molecule from butane to pentane to hexane. And the problem doesn't really change. Okay, you're just filling in what is at each of these positions, and the reactions are all going to be shown the same way. But it's just, if you don't know what's going on, all these details just doom you to making a mistake. You have to understand how the reactions work. This would even be a worse problem because I put a tritium in on the other side. So this would be a chiral center, this would be a chiral center, this would be a chiral center. Both sides are different, and so I would have 8 possible stereoisomers that could be resulting here, just from this picture right up here. Okay, so I have all the problems worked out. This is one of the problems here. I have an R up here. 1, 2, let's see. 1, 2, 3. Yes, that's R. And this one would be 1, 2, 1, 2, 3. That would be S. Okay, good. I see methanol, so I make the leaving group leave. I have a carbocation to show the SN reactions. Notice I come from the right side, I come from the left side. Initially I have this extra proton on here. Okay, I have just the base. I should use methanol here, not water, because we're using methanol here. So I'd have methanol come in and take that off, and I would have an ether down here. Okay, if I had used water, had water come in, I would end up with an alcohol down here. And notice this is R. The other possibility is I come in from the right side. I have that extra proton, I take that off. Excuse me. And I end up with the S configuration here. This is actually the same side as the bromine over here. Again, excuse me. These are SN1 possibilities. Remember, SN2 only one possibility, always from the back side. So we've doubled up the SN possibilities. Now, if I'm going to look at the E1 possibilities, leaving group leaves exactly the same. I make the carbocation, and now I got to look at every possible side proton. So now I'm just looking at the H up here on the ethyl part. I lose it from the left, okay, or I rotate around that bond and I lose it from the right, so I get two different alkenes. Right? In E2, that wouldn't be the case. In E2, I would only take this hydrogen off, push off the bromine, and these guys would be Z. But here I get Z and E. If instead I rotate the deuterium parallel to the p orbital lobe, I could do it on the left side, I could do it on the right side, and I get the same two alkenes, but now no deuterium. So here I have the same two alkenes with the deuterium. Here I have the same two alkenes without the deuterium, just by rotating this bond around. So I'm not doing anything real tricky. I'm just being very systematic and understanding how the reaction works. Now I have one more carbon that's to the side of this pi bond, and that's the methyl. It makes no difference which hydrogen I take or which side I take, because they're all equivalent. And so when I come down here, I get two hydrogens that are the same. And so this would be a monosubstituted alkene, a one alkene. Okay, so with methanol, this very simple molecule makes two ethers and five alkenes. Okay, what about if I use methoxide? So now the reaction has changed. I have a minus charge. So I'm saying this is an SN2 E2 reaction. So I can do all the same sorts of reactions, except the methoxide has to push off the leaving group coming from the back side. So I'm going to invert the configuration, and I only get one SN product. That's the only way it works. If I come down and look at the elimination products, I can only lose the anti-C beta H to drive off that bromine, because that's the only way I get the parallel orbitals to make the pi bond. So I could lose the H this way, or I could lose the H over in the methyl this way. Notice I can show them both in one molecule. So I get only two alkenes here. Or I can rotate the deuterium anti and lose the deuterium one way, where it's anti, and get this. So now, instead of getting two substitution products, we get one substitution product. Instead of getting five alkenes, we get three alkenes. Okay, so you can see the difference in the mechanisms there. All right. So this time, one ether, three alkenes, instead of 2 and 5. And that's where we're going to stop now. The third lecture I'll do a little bit later.